All right, so let me go over this match filter material one more time. So this is an open topic in the sense I'll tell you, there is still things can be done. It's a very difficult problem. So this is also related to so-called pulse compression problem. So pulse compression idea is whatever I wrote here. You see, you have an input pulse with some width t. You want to pass it through a filter. Filter is unknown, so that the output this gets compressed. So whatever is the waveform, if I call this output, it should look like this. So here the width is t. Here the width obviously want to be, I'm going to call it t out, capital T0 out. And it will occur at some point t equal to t naught. So T naught by T is the is the compression ratio, or the other way, or T over T naught. Of course, this will be larger than 1. T naught is the output pulse. Ti is the input pulse length. So you can take this as this should be as large as possible. So the question is, how do you do it? And remember, it's even worse. We need to figure it out. We need to, so if I call this a receiver or a filter, we need to find such a filter which is good for any waveform. Any waveform you, so look, think about communication. This is what is happening because you have signals coming like this and it's ridden by noise. So if you can compress the original signals like this, then you can hopefully, if the output is like this and still the noise is on top of that, you still can detect the bits. So that's the idea of, so the question is, how do you do it? So you can think of your own, I think now you know enough to think about this problem. So think of ideas. Of course, you can say that all you know is that if the transform of this is S omega, and this is H omega, then this output transform is of course S omega, H omega. But we want its inverse transform to look like this. And you can see its applications in radar, etc. So if you transmit a pulse of some length, and it goes and hits a target and comes back, and then if you pass it through a filter, H of t, you want it, the output to, I'll draw it here. You want the output to look like this. So this is going, this is coming back. And the reason is because if there is another object flying here, there is an object 1, object 2, then this waveform will come back from there also. So if this is the receiver. If the receiver is good, then you will see two pulses like this. If the pulse compression is not good, one pulse is going to come like this, other pulse is going to come. So you are going to see something like this at the output. So this versus this one, you can clearly hear. So here you are able to isolate the targets, whereas here it is not. So all this is because of the receiver. This is a bad receiver. This is a good receiver. Same thing in communication problem, right? As I said, information is coming on 1 and zeros, etc. And on top of that, this is riding on noise. So you get a waveform like this. So then you pass it through a filter H of t. You want the output to look like this. The spikes coming at the bits. So if you can compress the original pulse, and even if there is noise on it, I mean, still you can detect it by a threshold detector or something like that. So the question is, how do you do it? So this is in radar or underwater, wherever. So we will pose the way we pose the problem is, so you have a signal coming at you, but in all likelihood there is noise, right? So what is coming at you is something like this. This you want to pass it through a receiver, so that our idea is pulse compression. We'll say that so there will be two components here, the signal component and the noise component, right? So the signal component I am writing S hat, W is the output noise. This is the output noise. this is the output signal. Of course, you want this to be compressed like this. You want it to come out as a, then we have some freedom. We can say that I want the peak to be at a certain time. Peak at t equal to t0. So we can say that we want S hat t naught must be the peak. So this is going to be peak output power, right? I'm just querying the instantaneous value. So the idea is if it is compressed, it will be a larger value, right? And at the same time, we want the, so this is one goal. The second goal is minimize output noise. Because you can think there is always, so remember this pulse compression problem makes sense even without a noise. So you can ask a question, how do I maximize, what do I do to compress any pulse? That's why I said that's an open question. You can, so you have to play with its output transform. So the output transform, you can, if you want a pulse at the output transform must be as flat as possible, right? So you will begin to get ideas, right? So what I'm trying to say is if this is the input waveform and if it has got some transform like this, S omega, and the question is what is my H omega? So you can see ideas here because you try to fill up what like water filling, right? So if I can multiply by a function, some shape, whatever this shape is, so that the output is sort of where there is output is sort of like this. You see, if the output is like this, y of t, y of omega, then you know where I am going because if all this is in the frequency domain. So just to give you ideas. So then of course the y of t will be a compressed pulse because the inverse transform of a flat spectrum is a delta function. So that's the best. So the question is, how do you design a function? So clearly you can see this function, the receiver should depend on this because it's like pouring water, right? Wherever there is a large dip, you put in more energy here. So you can proceed. So if you have something like this, S of omega, then you know that H of omega should be what? Something the opposite way, right? So you want it to fill it up. So H omega, where the small gain, you have higher gain, and probably something like this. Right? Of course, if you change this shape, if you put in if there's a null here, this should peak here, right? So the idea is that if this is H omega, when you multiply these two, you want it to be flat everywhere. Then if this is the y omega, then y of t is going to look like, depending on the phase function, etc., y of t is going to look like this. So this is a compressed version of the original signal, right?
It has to do that for every possible input signal, right?
So you clearly can see there is no one function is going to do it, right? So right. Because it's like you only pour, if a plate has got some hole, you pour only just enough water depending on the shape of the. So one thing is very clear, as I said, this is so. For example, you can clearly say, why don't I multiply this as 1 over s omega, right? So it will depend on the filter will depend on the signal. That's very clear. But this is not practical because for example, the signal itself may have zeros somewhere and so on. This is where things get to be difficult because where you have zero, there's nothing you can multiply with and make it flat, right? Yes.
Yeah, I see.
Yeah. So that's why I said this is of course if the function is like this, a Gaussian function, then it's easy because I can multiply by a function like this, and this is h, this is s, and I can make the output more or less constant. But what if a function has got some zero spectrum? All this is in the frequency domain. But depending on the problem, but you may be able to see, this is where the noise will help. If you have noise here, noise will increase the floor, and there will be no zeros, and then you can work on it, right? So that's always an idea. And remember, we went through this in a sense. I gave you the spectral factorization and a whitening, right? So the whitening approach, except that this problem is for a deterministic problem. Simple thing, nothing stochastic here, just a signal. A signal is coming in, I want to compress it. What is the filter to use? A simple problem. But I'm saying now you have enough ideas to work on that too. So let me go to our problem, which is usually a signal, let's say a pulse, is buried in noise. So noise is here. So what is coming in is going to look like something like this. And we want to pass it through a receiver, Rx, so that there are two components. And I was saying that we want to maximize the output of the pulse at t equal to t0, and you want to minimize the noise power. So so you want to do this at the same time. So we could say I want to maximize S hat of t naught, or it's a square, and you want to, if you want to minimize, put the noise in the denominator. So we will put like this. And I went through the rationale before, because this is the average output mean square noise power, right? Why mean square? Mean is here, so I don't need average. This is mean. So think of Wt as the waveform. If you square it, you get mean squared, you get the square value. Then expectation is mean squared value. So that's like, we can take the root. I'm not taking the root. So that will be RMS. This is the mean squared power, right? Why power? Because expected value of Wt squared is RWW0. This is RWW0. And that, from what we learned, is the area under the output power spectrum. So this is certainly the average power. This is the average output to noise power. So we will call this SNR output. And that's this is the, of course, the input, the output to signal at t equal to t0. So the whole idea, you see, it's very cleverly done. Whoever thought about this, whole idea is that here we are not taking anything average, because we are hoping that the filter did its job and compressed the pulse, the output to be a pulse. And so really we only need to worry about, and the pulse is peaking at, so this is, we are assuming something like this. Peak is going to happen at t equal to t0. Because of this very constraint, the filter will be forced to compress. That's the hope. You see, this is how you train the filter what to do. You put your desire into the objective function. So our actual desire is to compress the pulse, but how do you express it? Compression. I gave you one idea before, which is multiply by a filter which will make the output flat. So you can try that too. I mean, the easiest answer is 1 over s omega, but 1 over s omega may not be implementable. That's the and usually you want to do it with a finite length filter. Otherwise, theoretically, the answer is, you say h omega is 1 over s omega, so that the output spectrum is flat and the output waveform is a delta function. All right, so I hope you got the idea of how we came. So mathematically, you want to maximize the output SNR, which is S of T, S hat of T naught squared divided by expected value of WT. WT squared, average output power. So this is S hat of T naught squared, and this is RWW0. But S hat of T is S of T convolved with the filter. So S hat of omega is S of omega multiplied by H of omega. So from here, S hat of T is the inverse Fourier transform of S hat of omega. So that's going to be 1 over 2 pi. The S hat of omega is S omega H omega e raised to j. So if I'm going to evaluate a T naught, this will be T naught d omega. So this is the expression we are going to use in the numerator. So this is the numerator expression, and the denominator expression is I'll come to it. So SNR output is 1 over 2 pi minus infinity to plus infinity S omega H omega e to the power j omega T naught d omega absolute value squared divided by RWW0. That will be 1 over 2 pi SWW omega d omega, right? We studied that. The output autocorrelation is inverse Fourier transform of the power spectrum. So evaluated at 0 will be just the area under the power spectrum. But output power spectrum is input to noise power spectrum multiplied by H omega squared. Another thing we studied a few weeks back. So I'm going to plug it in here. This pen is, let me try it. So this will turn out to be 1 over 2 pi S omega H omega e to the power j omega T naught d omega squared. Remember, we want to look at here. The square is only just to make it power by power. Otherwise, it will be voltage divided by power. So that's the reason to square it. And this is, and if Sn and omega multiplied by H omega squared d omega. And 1 over 2 pi cancels with 1 over 2 pi, and you get 1 over 2 pi here. Now look, let me assume the input noise to be white noise. So this is the white noise input. This is where I'm using the white noise. So this expression comes 1 over 2 pi sigma squared. Then you have the ratio of two expressions. This is H omega squared d omega. This is, I'm going to write S omega e raised to j omega naught t as one function multiplied by H omega d omega. The whole thing squared there. Any questions? So now in time domain or frequency domain, you should know Schwartz inequality. In time domain, same thing, AT, BT, DT. So notice that on the right side, it is energy of both AT and BT. So we are going to use this with A equal to S omega e raised to j omega T naught, B equal to H omega. And the equality is when one function b of omega is the complex conjugate of the other function. We'll have equality. In the time domain, bt is at or a star t. So let me use that here. So this is a, this is a, this is b. So using this, and to prove this, I think I have proved this for you. And so to use this, you'll get SNR output is in the denominator I have 2 pi sigma squared. Here h omega squared d omega. And here you have two integrals. First integral is s omega e raised to j omega t naught squared d omega. And the second integral is h omega squared d omega. So the key is this cancels with this. H is gone. So the numerator becomes simply integral from minus infinity to plus infinity. Remember, e raised to j omega naught t is a phase term. So this is just this, 1 over 2 pi divided by sigma squared. And the numerator is the same as from Parseval's relation. That's the energy of the ST. So that is 0 to t sigma squared. So this is E over S. This is less than or equal to, I'm sorry, here, less than or equal to E over sigma squared. So this is SNR input. So because of the noise, what it says is the best filter, what it can do is make the SNR output equal to the SNR of the input. Every other case, it's because of the noise. The noise will kill the signal. And as I said, there will be equality here when there is equality here. If you want equality, you need this condition. That means you will have SNR maximum will happen. SNR maximum will be SNR input, which is E over sigma squared. And that will happen when h of omega is the star of the one sigma. This is the complex conjugate of the other one. And if you remember the Fourier transform properties, that's the same as when h of t is st naught minus t star. Easiest way is take the transform of this. This will turn out to be s star omega e raised to minus j omega t naught. I think I did this for you. So this is the best filter. And so look at the filter. So the best filter depends on the transmit signal, as it should, because there is no one fit solution for all signals. You know, it's like saying your shirt should be designed with your body in mind, right? Or your eyeglasses, whatever, right? So the filter depends on the transmit signal, or the filter is matched to transmit, and that's how the name match filter comes in. Right? So what it says is, look at this. If the S of t is like this, what you do is first you flip it. So the signal, this is S of minus t. Then you look at here. Then you need to shift it. So if this is 0, here this will be 0 because you flipped it. Then you shift it, so it's going to be look like this. Right? You shift it by 0. And so this is st naught minus t, and that's your best receiver. That's what it is. So this is used everywhere. Communication, radar, underwater sonar, etc. Billions and billions of dollar designs based on this one idea. There is nothing better actually that works everywhere. This is so robust because you can see no transforms involved, easy to implement. If you know the transmit signal, then you can very well design it, right? And most of the problems like communication, of course, you know the transmit signal. There is nothing. It's only when you go to military applications, you may say, look, I don't know the signal, what signal is being transmitted. So look at this. You can find this in open literature. There are some French guys have so some unknown signal and noise is coming at you. Then what do you do? That's the whole. Anyone? Remember, so to design this receiver, you need to. Or what do you do in such situations? I don't remember exactly because, of course, if the signal is unknown, then you can't do anything. But you are capturing this data. So what you are capturing is signal is unknown, but this is your observation. Observation is ST plus some noise, right? So if the actual signal is something like this, maybe what you get is something like this because of the noise. So suppose this unknown signal is coming from a submarine, right, underwater. You have no idea, so you receive this. This is your observation, this one. So you can see this idea has been, you can find papers on it. I think some French have done this work before. So if you are capturing this in your own submarine, this one, right? You collect this. Then just to make sure what is going on, one idea is that, so step one is collect data. Step two is transmit it back. You see the idea? In other words, use this as at the next stage for you to transmit. So you are actually actively transmitting this signal, whatever you receive back at him. The idea is that this will act like a match filter because it will go and hit whatever is your unknown object that is transmitting this signal. Because usually this is coming from maybe some enemy platform or something. So that this signal S1 of T goes. And you can see this one, if this generated ST, this will act like a match filter. So you will get actually a better amplified signal, and that way you can figure out this idea, right? I mean, you can figure out what is the unknown signal. In other words, whatever you get, you transmit it back. Then you wait for the response, you transmit it back. And you can see how that works out. So this idea also can be, I mean, there are several variations of this. So the question is, how do you design the match filter when the signal is unknown, if you are in a hostile territory? Anyway, I can go on and on, but I'll stop this here because I want to cover two more topics. And other idea is, as I said, you should remember whitening filter for a stochastic process. It's not the same as flipping something. So you have X of T. I want to design a filter here, right? HFS or HF e to the power, depending on discrete or so that I have output process whose spectrum is flat. So everything depends on this relation. Output spectrum is input spectrum multiplied by the transfer function squared. So if you want this to be flat, the output filter, which is HSF H star of S at S equal to j omega, or same as S squared equal to minus omega squared, must be equal to 1 over Sxx omega. So we should be able to write the spectral as the square of a function. I went through this, right? And you want that filter to be, so if I can write Sxx omega as g of S multiplied by g star of S, with where S squared is minus omega squared or is equal to j omega, then if this filter is stable together with the inverse, that's what we call it to be the spectral factor. And the job will be done by this will be 1 over g squared, so that the filter you are looking for is 1 over g of S. This is the whitening filter, right? But because the filter is stable and its inverse is stable, the whitening filter also will be stable. So you see, now you can couple these two ideas, right? Which also we have done before. So if you have a signal coming in, a colored noise, so first you worry about the, so let's say this has got some, so you find out the filter corresponding to this, and you do a whitening filter. So the noise is written as GS omega. So as a result, the signal will change it to some new signal plus white noise now. Then you design a match filter for f of t. So that will be this. So this together with this is the total. So always the mantra is whitening followed by match filter. Remember, when you whiten, you are not matching it to the original signal, you are matching it to whatever is here at the input. But this is, top to bottom, this is the only idea in any signal processing discussion, whitening and match filtering, at least in linear filtering. And so pulse compression in presence of colored noise, white noise, no noise. So you can see its topics are endless. There are some results available, and you can also try to try to sort of work on these problems. Any questions on match filter?
Professor, how to know the G of S?
All right, so you have to know, you have some idea of the, let's say I'm saying the noise spectrum is, remember we went through this. We may make some measurements and so on. Somebody says the noise has got, noise looks low pass, okay? So you have to make this observation one way or the other way. If I make this observation, I see that I can write this as like this. I went through this last time, right? At S equal to j omega. Then this filter is just my G of S. You see it?
Okay, so is it based on some measurements?
Whatever. Measurements or, yeah, ultimately everything is based on measurements, right? Or you may say, look, I have reasons to believe that by observations or you do some experiments or from theory, you know, you can figure out the autocorrelation function of the noise process. Then you do the Fourier transform, then you get the spectrum, that will give you, and then you do a factorization. That way you get the G of S.
Okay, I see.
Right, but some work has to be done, right? One way or the other way you have to use something, right? So you collect the data. From the data you can do autocorrelations and then try to fit the autocorrelations into something, into a good model. So let me talk about the, sometimes you may have reason to believe that the noise is an ARMA process. So what is an ARMA process? So let me talk about that. So if you can fit some model into the data, then the spectral factorization and finding the G, etc. becomes easy. But then you have to have some good reason to put to that model. So maybe sometimes the physics will let you know what the model is. Otherwise, always data is the king. You have to observe a lot of data. And let me tell you the hard way. You observe a lot of data. From the data you observe, estimate a lot of autocorrelations. Remember last week we went through ergodicity and how to estimate the autocorrelations. Once you estimate a large number of autocorrelations, you can compute the spectrum. But then you have to make sure that the spectrum is non-negative. Once you get the spectrum, you can do a factorization and get this filter. Then you flip it, you will get the whitening filter. Is that clear?
Yes, thank you.
Yeah, so you have to do some work. So as I said, you get data, then you can find out estimate autocorrelations. I'm not saying this is necessarily the way, but conceptually. Or you can fit in a model and go from there. And from here you find the spectrum. Then you use the spectrum to write the factorization H omega, H star omega. Then Hs of omega or 1 over H is the whitening filter, right? But you can come through the model also. But question is, how do you fit in a model? Once you whiten the filter, it becomes a white noise problem. But otherwise, sometimes you may have reasons to believe that the noise is already white. Okay. Any other questions? Hello? Anyone there?
Yes, Professor. Everything was clear.
Yeah, very good. So let's go to one important model that people use all the time. So you have a stochastic process. This is just one realization, sampled stochastic process. So I'm going to call this Xn of t. This is, I mean, you have several realizations like this. This is just one realization. Sometimes for you say that the current value sometimes Xn depends on previous past values. There may be situations where, for example, today's temperature, right? Definitely it will have some influence on yesterday's and a couple of days back. I don't know how many days back, right? Or more generally the weather. We certainly know tomorrow it is not going to snow. And tomorrow is not going to be 90 degrees either, because in the past few days is generally what we have found that it was 60 degrees, 58 and this and that, etc. So there is a dependency on the past, recent past. Right? So most of the there are some stochastic processes with a dependency on most recent past. I mean, your health, exactly the same thing, right? It depends on what you have been doing, so how you live last whatever, years or etc. So we want to put this into a mathematical form. So this is one way to say this. So this is a sampled stochastic process. Look at what I have written. I have written that Xn, the current value, depends on previous values. So this is how we bring in the past dependency. It's only the most recent. Of course, you can go by increasing p, you can go as far back into past as necessary, as you feel necessary. Remember, there's nothing stochastic here because it's all xn. So it has to depend on some noise, some other stochastic process also. So generally, I'm going to write it like this. So it depends on some other process also. So you could think of this as noise. So whatever is happening, whatever is the signal that you are interested in, it depends on its previous values, but then there is all sorts of other things messing it up. So there are two processes going on. You can call this the noise. By noise, I meant whatever you are not interested in. That's sort of the noise. Even that is, we are only using Q samples from the past. P and Q can be equal, doesn't have to be equal. And so this is one way to model a dependency on the recent past. And this is universally used. So this is known as ARMA. What does ARMA stand for? Notice here, this is like a regression because xn depends on its own auto regression, right? xn depends on its own previous p values. Auto is because xn depends on itself. Xn doesn't depend on yn. Here xn depends on yn or wn, so that's not auto. But if you look at here, what is going on is this is like a moving average, right? If wn is a process like this, if this is wn, then what you are doing is you are taking a window of q values from 0, and then you are wn minus k is just going back. Then you are shifting this window here, 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 etc., and averaging, right? So if you average all this, so this is the moving average part. So that's how the name comes in, auto-regressive moving average, ARMA. So we'll write here P comma Q. So the auto-regressive part has got P, and moving average part has got the Q samples from. So you can see this is a process with memory. On itself, you have a Q tap. You can easily implement this using P and Q taps, right, on Xn and Wn through delays and so on. So forget about this course. If you just think of this as a deterministic class, then let's look at that equation one more time. So I want you to pay attention here. Here there is no point in putting I equal to 0 through P because I equal to 0 will be Xn. So this index only runs from 1 through P, the regressive part. Here, of course, I can put any, I can include the current. In other words, the current value depends on the current value of the noise. Otherwise, you can go from I equal to 1. We just put B not equal to 0. So here it goes from I equal to 0 through Q. Here it is 1 through P. Let's take the Z transform on both the sides. Remember, Z transform is you multiply by Z raised to minus n, sum up. So that's going to be X of Z. So you can see X of Z is here, minus summation. Here you have AI Zi, right? You know how to go do this. You multiply by Zn, then make it n minus I. So that also multiplied by X of Z. Plus here this will come out to be Bi Zi W of Z if you do the Z transform. So if I collect X of Z, then you have 1 plus sigma AI Zi is sigma bi zi multiplied by w of z. I hope you found, maybe I should do this step so that you have this equation. Xn, I'm going to multiply by Zn. So on the other side also, I have what is it? Ai xn minus I Zn plus summation bi w n minus I Zn. Now, then I'm going, this summation is on I, this is on I. Then I'm going to do summation on n equal to 0 through infinity. Or this is what I'm going to call x of c. So I'm going to do a second summation here, n equal to 0 through infinity. Another summation here, n equal to 0 through infinity. And here instead of Zn, I'm going to add and subtract I. Here also add and subtract I. So you can see this one I can write aizi, and this one I can write zn minus I multiplied by xn minus I. But this is, you change the variable, this is back to x of c. And there's a minus sign here, and this is x of c. On the right side here, plus summation bi zi and summation w n minus I multiplied by z n minus I. As I said, you put n minus I to m, this becomes m, then the summation becomes m, this you get. So this will become wmzm, that is capital W of z. This is I equal to 0 through q. I'm going to call it b of c. So if I bring this term to this side, I get x of c multiplied by 1 plus summation aizi, I equal to 1 through p equal to bzwc. So I can write this as an input-output relation. So this I can write, see, let me bring this term here. So I get output over input equals b of z over a of z. Let me write it here. So I can write it like this. Right? So it looks like I can have a function here. Input is w of z, then the output is x of z. Remember, this is not a stochastic process. I'm just doing a regular signal. So x of z is h of z multiplied by w of z. And what we got in the previous step, you look at here. I'm going to copy this there. What I got, this is, we had there x of z equal to something, which was bc. That was b0 plus b1z plus etc. bq cq. And here 1 plus a1z etc. apzp multiplied by w of c. So you can take this to be the filter h of c. So h of c looks like the ratio of two polynomials. The numerator polynomial is b1 plus b0 plus b1c etc. bq zq. This is 1 plus a1z etc. apzp. So this is bc over ac. So this is a transfer function corresponding to an ARMA system. So this has got z minus z1, z minus zq, q zeros and p poles, z minus, let's say, lambda 1, etc., z minus lambda p.
Professor?
Yeah.
Why is it a multiplication and not a convolution?
Remember, this is all in the, I just showed you, right? Hold on. Remember, it is what it is. Do you know Z transform?
Yeah.
All right, if you know it, look at here. We start with saying that This is the model, good or bad. We are saying, I explained to you the logic. Take some stochastic processes which depend on the past. That's where we are starting with, okay? That's physical, right? I just explained you how it is. Everything seems to have dependency on its past, right? Almost everything, right? In nature, right? So we want to model that. That means it depends on its own past. Today's weather depends on previous few days of weather. There is a real dominance. It's not going to depend on December weather, right? You definitely know, because December weather was completely cold and snowy, etc. So this relation is, you will say that many places this relation makes sense. Now, if you take a transform of that into the Z domain, you get this picture. You get here. So this is the same as, of course, to answer your question, this relation can be written like this, but in time domain, you have an inverse transform H of n. Here you have W of n. Here you have X of n. Of course, you are right. So X of n will be, if that's what you are asking, X of n will be, so here you have H of n, here you have W of n, here you have X of n. Remember, you can certainly write it like this. The output is Wn convolved with H of n, if that's what you are asking for. You can write it like that. But we know that what we started with is this model, that I don't want to lose the model. So this is the real model. If you want, you can write it like this as a convolution. So X of n, of course, can be written as sigma hk x n minus k, k going from 0 through infinity. But here the problem is there are infinite number of values here, whereas this is only a finite order model. So your system only has a finite order model. It is B0 plus B1z, etc., BQZQ plus A1Z, etc., APZP. So two ways to look at this. You want to write it as a convolution, it will be an infinite convolution. But if you can also write it as in terms of this, what do you call, regression into the past, into the recent past. Then you are only using P samples here, Q samples here. Here you are using all the samples from the past. Pick your choose.
I don't think I can see
Pick which one are you. What? What is it?
I don't think I can see the screen clearly.
What did you say?
Yes, Professor.
Wait, what is the problem?
The screen is
Professor,
not
I think
clean.
your video quality is
The
really
screen
low.
is not.
What?
It's a bit blurry.
You can't see it now? I can see it.
The screen is
Yeah.
not clear right now.
Tell me if it is becoming clearer. Not good.
I think it might be related to the connection, not the focus.
What connection? Maybe I'll change over to the other pen.
Very.
No, it's not working. How about now? Did we lose you, Sushant?
Yeah, I think there's some problem with your Wi-Fi.
Yeah, Professor, on my side, it says your video quality is reduced because your bandwidth.
Why is it suddenly an issue?
Internet connectivity issue.
Yeah, we are almost done. Anyway. But can you see anything or you can't see anything?
Lag in the video, but audio is
Can
clear.
you like make your handwriting bigger?
Yeah, I'll change it to some other pen. Can you hear me at least? Can you hear me or no?
Yes, Professor.
Yeah,
Hello?
audio is clear.
All right, so as you said, as I was talking about you to you, this is our real model. This real model is physical because it only uses P samples from the past and Q samples from the noise. But you can also write this as like this if you want. You can avoid the noise by writing it like this. Obviously, this is a convolution between hk and x of n, hn and x of n, where h of c comes from here, b naught plus b1c, etc. Sushant,
Yes, Professor.
can you read it what I'm writing, or you can't see this either?
Like it's not completely clear, but yeah,
Maybe you have some eye problem. Why is it not clear?
the
All of
video
you?
quality.
Yeah, let me see. I mean, video is all good. I don't know what else to do right now. Anyway, we're almost done. So, uh, so we can call this to be, this is what is called an ARMA system. So this is the system. These are the system parameters, the A's and B's. So usually the problem is, now think of this as a stochastic process. How if xn is a stochastic process, how do you find the parameters from the data? That's the problem. I'm not going to completely do it, but I'll give you some ideas. So one assumption you can see that, of course, I'm going to define, let me define expected value of x and x n minus k, t1 minus t2 to be rk. So these are the covariance of the process. This is your data. These are unknown. The A's and B's are usually unknown. So the big question is, if I have a stochastic process, if I measure some data, how do I find out the ARMA parameters A and BI? That's the problem. We are not going to completely solve it, but I'll give you some ideas. And one assumption is that the new noise has nothing to do with the past data. Look at here, the current data only depends on the previous values of the noise. So today's noise is not going to affect tomorrow. Like whatever is the noise at this point is not going to depend on the future values. So this is zero. This is one assumption. Old data is only affected by yesterday's data is only affected by yesterday's noise. Yesterday's data is not affected by today's noise. That's a reasonable assumption. If that is the case, let me compute RK. So RK is expected value of xn minus k star, and I'm going to expand for xn. So this is minus sigma ai x n minus I, x n minus k star, expected value is here, plus sigma bi or w n minus I, x n minus k star. So you can see this is T1 minus T2. So that's R of k minus I. So I hope you can see that Rk is minus summation Ai Rk minus I goes from 1 through P, plus this junk. So let's look at this carefully. You can see here I goes from 0 through Q. So if this K is even before Q, as I said, the recent noise doesn't affect the past. So you can see this term will be 0 if K is greater than Q. Think about this, just exactly the same reasoning I mentioned here. So that's the key. Otherwise, there will be some correlation between xi. But if k is our running variable, if k is greater than k, minus k is less than minus q, then all the noise becomes more recent, right? And that recent noise doesn't affect the past data. As I said here, recent noise doesn't affect the past data. So this will be 0. So let me bring everything to one side. You get, so for an ARMA system, this is the important relation. And the covariances and the A's have this relation. Sigma AI Rk minus I is 0. So certainly if Q is less than P, we can say that is true with K greater than or equal to, K greater than Q is the correct one, but all these three statements are correct. So then you can sort of start writing equations, right? So this will be, everything will be equal to 0. So let's start with the K equal to P, and you flip the other way. In other words, start with AP here, then AP minus 1, etc. A1 and 1. So AP, if K equal to P, K is P, I is P. I'm coming from the top end. So that will be AP R0, then A1 R, remember K is P, I is P minus 1. So this will be R1, R2, etc. K is P, I is 0. So this will be RP. And the next one will be K is P plus 1. K is P plus 2, etc. You can write all of them. So when K is P plus 1, so this will be R1, this will be R2, etc. RP plus 1, right? Because look at here, when K is P plus 1, A0 is 1. So P plus 1 minus 0, so that's RP plus 1. Then K is P plus 2, K is P plus 2, P is, I is P. So this will be R2, R3, etc. RP plus 3. So you can go infinite number of equations. Let's say RP, etc. R2P. This is P plus 1 equation. You can get more also, RP plus 1, etc. R2P plus 1. You'll get an infinite set of equations. Now you can play with these equations and solve for this. For example, if you take P plus 1 equations, you can solve for A1 through AP, etc. So you can see how you can find the system from the autocorrelations system. So this is going back. So you measure the data, you assume ergodicity, you compute the autocorrelations, then use these relations. Remember, this is a Hankel matrix. All these entries are the same. So there is a theorem by saying that if you create a large Hankel matrix, So let me call this to be Rn or something, so a Hangel matrix of size. I'm sorry, this will be 2n, right? 2n minus 1. So this, if you create such a Hangel matrix, you can see there are rank conditions, because look at here, all the Ris are they only have a p relation. If you take the columns, the pth column is linearly related to the p minus 1 columns, even if you put more columns, because this relation is true. So in a matrix like this, its rank is going to be, rank of any Hn will be p. That's the whole point, so long as n is greater than or equal. So you can create these Hangel matrices and look at its rank. So at some point the rank will keep increasing, then the rank will stay the same. That will give you an idea about where will be p, etc. So a lot of ideas on how to go across finding these are all research problems. Almost everything has been done, but there is always something new to do. So what was the problem? So you can see, you can use you use p plus 1 equations from here. You can solve for these p unknowns. Right? Actually, use p equations from here. You can solve for these p unknowns. So you get the denominator. Then similarly, you can compute in some other ways. You can compute the numerator, which is harder. But at least I showed you how to get the p. Remember, usually you only have data. You don't even know what is the value of p and q. And here you can see now, if you begin to plot the rank of these Hangel matrices created from covariances, they will flatten out. So everything is not obvious. You have to sort of look into the details. Any questions? So, anyone on this? Sushan, is the video good or bad now?
It is still bad. Like there's some problem with your internet connectivity.
Is it readable or no?
Like yeah, it's readable, but
you
not
read what?
like small words aren't readable. So this is a matrix with R1, R2, R3. Rank of Hn equal to P.
That's good. Oh, anyway, I am almost done. Let me come to this Fourier transforms. I was going to do some Markov chains, etc., but it's sort of getting late, and also it's to be in some other class. So remember, if you have a time signal, we want to go into the frequency domain. That's the whole point. So f omega is defined as ft e raised to minus j omega t dt. Are you there, Healing? You asked me a question. Where are you? The student who asked me a question, are you still there or you're gone? And the inverse relation is this. So let's do the Fourier transform of a delta function. What is it? So that's pretty clear, right? So this is going to be delta function multiplied by e raised to minus j omega t dt. So delta function multiplied by any function is evaluated at the t equal to 0. So this is turning to v1. So this is the key expression. So if you look at the inverse transform, we have ft equal to 1 over 2 pi minus infinity to plus infinity what is it? F omega e raised to j omega t d omega. I am going to replace this t by u, both the sides. So you get small f of f u is 1 over 2 pi minus infinity plus infinity f of omega e to the power j omega u d omega. Now I am going to replace this omega by some other variable. Let's say I use v. So this will be v, this will be v. So I'm going to rewrite it one more time here. So this is minus infinity to plus infinity f v e raised to j v u d v. Now what am I going to do? Watch what I'm going to do carefully now. I am going to replace this u by omega back to, I'm going to use some other variable. So I get small f of omega is 1 over 2 pi minus infinity to plus infinity f v e raised to j v omega dv. Now finally I'm going to replace v by t because v is a running variable there. So in this relation, f omega is, or I'm going to bring in 2 pi here. So I have minus infinity to plus infinity ft e raised to j omega t dt. But this almost looks like Fourier transform, except there is, this should have been minus. So I'm going to look at this expression for f of minus omega. So then this will be ft e raised to minus j omega t dt. So you look at this relation. So we get a key relation. Ft, the transform of ft, this waveform is 2 pi multiplied by f of minus omega. So using this, because the transform of delta t is flat, if you bring in this function here, this will be 2 pi multiplied by delta of minus omega, but delta is a symmetric function. So you get the delta of omega. Now what? All right, now you wanted to know, let's see what happens to ft e raised to j omega naught t. So the transform of this is ft e raised to j omega naught t e raised to minus j omega t dt. So that is ft e raised to minus j omega minus omega 0 t dt. So this is nothing but the transform evaluated at omega minus omega 0. So you get this relation, ft transform is capital F of omega, then ft e raised to j omega t naught is f of omega minus omega 0. So ft e raised to minus j omega t naught is f of omega plus omega 0. So if you add these two, you get, if you add these two, you get ft multiplied by 2 cos omega naught t. Oh, 2, what happens?
Professor, on the left
yeah.
side, the t0 should be omega 0.
I made a mistake. It should be omega naught t. So this should be omega naught t. I have it correctly here. So this should be omega naught t, omega naught t, omega naught t. Right. So that's going to be f of omega minus omega 0 plus f of omega plus omega 0 divided by 2. Similarly, if you take the difference, you will get a 2j sine omega. So I'll write to that too. So you get ft sine omega naught t. The transform is f of omega minus omega 0 minus f of omega plus omega 0 divided by 2j. So remember, your question was, we had one has a transform of 2 pi j omega. So from the previous relation, cosine of omega naught t will have a transform. You divide this by 2. Delta of omega minus omega naught plus delta of omega plus omega naught divided by 2. So the transform of sine omega naught t would be delta of by, I'm sorry, pi, I guess, right? There's a 2 pi here, 2 cancel, so there will be a pi here, there will be a pi multiplied by j or minus pi j. If you want to absorb the minus inside, you can write this way also. Pi j. So I hope this is how you find the transform of cosine and sine. What else you want me to do? Anybody? Please, even if you don't do today's problems well, please, I'm going to again ask one problem like this, like today's quiz, next week. So please, whatever you haven't learned, please learn how to do this, how to use these properties, etc. Everything you should not be taking it by heads on. You see, that's a bad way to approach solving problems. You have to sort of try to make use of the properties. That's the way I designed the test today. Anybody? What else you want me to cover? I'll just mention one result, which unfortunately we don't have. This itself should be a course by so these are random variables. If you have a set of random variables, so remember, this is the conditional density function of the current state depending on the previous states. If this is the same as like this, what means is that even if you give me all the previous states, it only depends on the most recent past. So in other words, these are processes with one-step memory. So there are a lot of phenomena where only the most recent step matters. So the conditional density function of xn, given all the previous random variables, we can think of them as the previous states. Depends on, is completely characterized by the density function of the same random variable given the most recent past, xn minus 1. So obviously this is like one step. So one step memory, processes with the one step memory. These are called Markov property. So you can have continuous time and discrete time. I gave you an example of a continuous time. On the discrete time, I mean, this is discrete time. Continuous time, it will be like this: xn less than t given all the xn minus 1, x of t less than t is the same as xn given just the distribution function of xn given just xn minus 1. It only depends on just the previous value. Now, let me just summarize why this. So, you can see a lot of things that we do also. All that really matters is the most recent past, right? So sometimes, a system only has a few possibilities. So it jumps around from there to here. Right? So if you call each one to be x1, x2, so it just goes from everywhere. Let's say everything is possible. It can jump around, right? So this is a closed system. Right? So corona, it is like this, right? So healthy, you get sick, but most of the people get healthy back. Some sick go to hospital, but then they become healthy, or they whatever, they die. So healthy, still homesick. I'll call it homesick. So from hospital, sometimes they go back. Still, they are not completely healthy. You go back there, but from there here you can come here, and so this is unlikely. If you're healthy, there is no reason to go to hospital, and if you're dead, you are not going to come back to nowhere, right? So this is like a absorption state. It's nothing comes back from there. So in general, you can say, so these are the different states. So think of any problem. You can, if you simply toss a coin, there are only two states. So if it is head, if you toss a coin, you can get a head back, or you can go to tail. So if it is a head, the next toss, you can get a tail with the probability Q. If it is a head, you can get the head with the probability P. So only two states, right? If it is head, you can go to tail with the probability what? Q. If it is tail, you can come back to head with the probability P. If it is tail, it can stay there with the probability Q. Here it can stay there with the probability P. So the question is, similarly here, I'm going to call these probabilities Pij. This is Xi, this is Xj, and I can call these probabilities Pij. So you can see that I can create a matrix P11, P12, etc., P1n, Pn1, etc., Pnn. You can also see that from any state, it has to either stay there or it has to jump somewhere, next stage. If you are healthy, you can remain healthy, or you get, there's only few options. If you're healthy, you stay healthy, or you get sick, or you end up go to hospital directly. You can also go to hospital directly. Now, which usually doesn't happen, right? You get sick and then you go to hospital. So this probability is 0. If you're healthy, you're going to hospital unless you are crazy, right? You're not going to go to hospital. So you're from empirical model, you look at the New York City data, etc. You can compute these probabilities. But let me tell you a main problem which you can understand. Anyway, my whole point is, you can see that this matrix is, let me call this to be the probability transition matrix. Remember, now I'm not teaching you, I'm just telling you a story because we mostly just ideas. Anybody has a guess what happens if you add up all these probabilities in each row, the way I said? Anyone? What will happen? From any state, one, you have to go to either 2 or 3 or stay there, etc. So if you add up all these probabilities, what will you get? Anyone? If you row sum, look, physically think about it. As I said, from any state you only have few options. At the next stage you can stay there, or you go here. Yeah, it will be 1. So a probability matrix has this property. A probability matrix, all the probabilities are non-zero. So any probability matrix only has 2 properties, stochastic matrix. Non-zero numbers that each row adds up to 1, because from any state you can, at the next stage, either you stay there or you go to another state. So a question with the states is like in Corona, we want to know what happens after 1 month or 1 year, 2 years. What happens to all these people? Remember, the picture story is very simple. If you are healthy, you remain healthy with a certain probability, or you become sick with a certain probability. So you'll have to figure out these numbers. So let me call this state X0, X sick, X hospital, and this is a bad state, death. You don't come back then, right? And so the question is, if you are running around here, how does the system stabilize? So there is a theorem. I'll just mention the theorem. And maybe in a later course, if I catch up with you, we can go over this. This is in my book, chapter 15. So the theorem is that, of course, you can see everything will be controlled by this matrix. So if you can get this matrix for the corona matrix, then you can figure out what will be the, ultimately what will happen. So ultimately, this is the beginning of an important process. Markov chains are used everywhere. And it's a shame we haven't even, I wanted to cover the basics. But with all these problems, it's becoming, so we look at, you look at its SVD. So this is where the matrix analysis will become clear. You look at its eigenvectors. I think, did I forward you? I think so. Like maybe I mentioned to you about this Perron-Frobenius theorem. Maybe I did forward you a paper I wrote long back, I think. Anyway, you can find it from the internet if you type in this name, Perron, P-E-R-R-O-N, Perron-Frobenius theorem, and its applications in wireless. Same thing, this theorem is, anyway, you look at its eigenvalues and eigenvectors, one of the eigenvectors will turn out to be non-negative, and that will tell you the probability of the system remaining in different states in the long run. Remember, the question is what happens in the long run? So that question needs to be answered. It will come out from a eigenvalue decision of this probability matrix. Let me give you another problem before we go away. So look at this wireless. I don't know how many of you have. So the question is, how do you control the power in your handset? So you have, you are talking to everybody, so many users, right? X1, these are users, different users, right? So you have base station here, and say you are transmitting power P1, P2, P3, Pn, etc. Right? So question is, how much power to transmit? So you can see if everybody is transmitting more and more power, because you may be only talking to this person. So if you increase more power, you are going to, remember, you are going to contaminate everybody. There will be crosstalks and so on. So there will be noise. So then the other person has to increase the power. This is the same problem when you go to a restaurant and having dinner, you talk to your buddy, then the other guy feels your talks a little louder, then you have to talk louder, etc. So the same problem. So the question is how much power to transmit. All these are same power to transmit. A completely different problem, but the equation will turn out to be exactly the same. So you look into my paper. If you type in Perron-Frobenius theorem and my name, you will see the paper. It's available in free, so you can read it there. But I'll give you an idea how it is solved. Say you are talking. Say you are talking to this guy. So there is some. This is Pi. This is Pj. Pj. So most likely the way it goes, you know how it goes. The thing goes through the base station. So I don't remember exactly, but let's call this each of these to be HIs. HI is the path loss towards the base station. HIJs are the interferences to the other users. So what you want to do is you want to maximize this. This is the power, your power at base station, right? Power received at base station. You want that to be high, and all the other, this is the plus noise, right? So you want this to be, this is the interference power, right? You want this to be, so whatever you call it, let me call this to be rho. You want to maximize this quantity. So if you rewrite it, again, you go home and do all this stuff, you will come out with an equation like this, where this will be HI, I don't remember exactly, but you can rewrite it. It will be all positive numbers here. And you have to essentially solve, this is how the problem in wireless is, your cell phone is, power is controlled through this power control equation. Again, my point is, again, you come up with a Perron matrix, which is a positive matrix but a probability matrix has got all the rows adding up to 0. But anyway, so you use the Perron-Frobenius theorem to solve this problem also. Or inventory problem, right? In operational analysis, Amazon or whoever has got goods here and there, you have to move them from one go down to the other go down, right? By minimizing some cost. But whatever you are moving is not a negative number, a positive number, right? Some measure. So again, you can put it into this form. You have to maybe you want to move the maximum quantity and you want to minimize the cost, right? Remember, there is cost associated. So you get a numerator and denominator, and you have multiple locations. You want to maximize it for everywhere. So that's how a matrix comes in. You don't, and then when you put it in, you will get a common solution. So there is, you can see a matrix makes use of the feedback from different sources. Anyway, without getting into detail, I can just keep talking about it. All I wanted to do was at this point that with your current knowledge, you can dive into Markov chains. Another thing is, if sufficient a number of you come up and sign up for a selected topics course, I can offer all this, especially the Markov chains and the system identification as a selected topics course. I mean, maybe not next semester, but semester after next. But I need at least 8 to 10 students. So some topics we have not covered is how to find out all these ARMA parameters in detail, and also what I just discussed. How do you study the evolution of a system with multiple states? And we can do the population control analysis, this and that. But so you have the background, except we don't have time in this course to proceed. Good for you or bad for you, I don't know. But as I said, if you are interested, get me 8. If 8 students come to me, I will put in a request for a selected topics course. But it's your responsibility to show me 8 students, somebody. But I gave you a good exposure to both the probability and stochastic aspects. Any questions? Otherwise, we'll go to the exam. Tell me, somebody, do you want me to answer anything else? Anyone?